Okay, good morning, everybody. Government Degree College, Shadnagar invites you to watch video classes on mathematics subject. The Department of Mathematics prepared different type of video classes, and it is a video class for final year. The topic name is vector space, which is in fifth semester, and it is 12th lesson now. And these video classes are prepared by myself. My name is T. Sri Krishna. I am assistant professor of mathematics in the college now. Okay, in previous 11 classes, we completed the following important points. Okay, just we check out what are the points we covered in last classes now. First one is basic concept, that is vector space and vector subspace. What is the two definitions we will discuss, and similarly linear sum of two subspaces also now. Now we'll discuss what is a vector space means now. It is a basic concept. Okay, everyone should know what is the definition. Now V is a set of non-empty, it is a non-empty set of vectors, and F is a field now. Okay, scalars are comes from F and vectors comes from V now. With respect to the internal composition, that is vector addition, we should satisfy all abelian group properties. And with respect to the external composition, we should satisfy scalar multiplication properties. Then we can say V is a vector space over the field F. Now after that, now what is the subspace means now? V of F is a vector space and W is a subset of V. W is a subset of V. If W satisfies vector space properties, then we can say W is nothing but now is called vector subspace of V. It is nothing but now vector subspace of V now. And what is a linear sum? Now W1, W2 are any two subspaces of V of F. The linear sum of W1 and W2 is nothing but now we can express as W1 plus W2 is becomes now linear sum. Every vector of W1 plus W2 is in the form of alpha plus beta, where alpha is belongs to W1 and beta belongs to W2 now. That is the condition now. After these definitions, we have algebra of subspaces now. What is the algebra of subspaces now? When two subspaces are, there are two subspaces, W1 and W2 of the vector space V of F, then intersection is definitely is a subspace of V. Intersection is definitely subspace of V. When union is subspace of V of F, there is a if and only if condition. W1 is subset of W2, otherwise W2 is subset of W1 now. One of the set should be subset of the another now. Then only we can say W1 union W2 is subspace of V now. Now after that now, this linear span condition now. Now V1, V2, Vn are vectors in V. The span, okay, that is L of S. The span V1, V2, Vn is a subspace of V. Therefore, span of these values, that means linear combination, all possible linear combinations of V1, V2, Vn is a subspace of V. And the next definition, null space and column space now. What is a null space means? If Ax equal to 0, then X is belongs to null space. That is a basic definition, simple definition now. What it is now? What is the meaning of null space? Null space of an m by n matrix capital A is here now, m by n matrix now. The null space is denoted by null A, okay? And what is a null A means now? It is a set of all solutions. It is a set of solutions now. Now, what the equation? The equation should be homogeneous equation. What it is now? Ax equal to 0. The set of all solutions of the homogeneous equation Ax equal to 0. And next now, column space now. What is the definition now? Column space of an m by n matrix capital A, it is nothing but now it is denoted by column A like this now. It is a set of all linear combinations of columns of A. It is nothing but now set of all linear combinations of the columns A. That means if A contains n columns A1, A2, An, the column A is nothing but now span of A1, A2 up to An. It is a definition for column A now. Okay, now. Next now we'll start today class now. Today we'll discuss different type of problems now. What is the first problem now? Capital A equal to 2 minus 2, 3, 4 minus 5, 7, minus 2, 7, minus 8, 1, 3, 6. It is a given matrix capital A now. Now here now we want to prove now V equal to V is another column matrix is given now. The elements are 3 minus 1, 3. Determine if V is in column A, null A, could V be in column A now? Whether V is belongs to column, null A as well as column A. Okay. The given matrix now. The given matrix order is 3 rows and 4 columns are there. Okay. 3 rows, row 1, row 2, row 3, column 1, column 2, column 3, column 4. 3 rows and 4 columns. Therefore, it is a 3 by 4 column, matrix order now, 3 by 4 now. Now here A contains 3 rows and only 1 column. It is a column matrix now. Now here we have only 3 entries. 3 entries. Okay. And generally, null A is a subspace of R4 now. Number of columns are 4. Therefore, null A is a subspace of R4 now. And here R4 contains 4 entries. But V contains only 3 entries. Therefore, V is not in null A. V does not belongs to null A. V does not belongs to null A. Now, next verification, whether V is in column A or not. What is the condition? If V contains solutions, then we can say V is in column A now. Now first I am taking augmented matrix now, A and V, A matrix and V. Complete A matrix, first 4 columns represents A matrix and the last one is represents V matrix. What are the columns now? 2, minus 2, 3, 4, minus 5, 7, minus 2, 7, minus 8, 1, 3, 6, and the last column it is nothing but now V, 3, minus 1, 3 now. Okay, these are the values now. Now the leading coefficient should be 1. The leading coefficient should be 1. It should be 1. Therefore, how it is possible, how to get 1 here now? 2 to jump 4, minus 3 is nothing but now 1 now. Now, therefore, I am changing this entire first row, okay, multiplying the first row with 2 and subtracting the third row now. Then 4 minus 3 it is becomes now. Now, therefore, 2 times of 2, 4 minus 3 is becomes 1. 2 times of 4 is 8 minus 7 is a 1. Next value, it is minus 4 plus 8, that is a 4. And next 2 minus 6 minus 4, 6 and 3, 3 now. Therefore, the first row is becomes now the first row is becomes now 1 1 4 minus 3 3 now. We are applying this operation here in first row now. In first row we are applying operation. What it is now? 2 times of R1 minus 3. Okay. With the help of this operation, we are converting the leading coefficient as 1 now. Next now. After getting this one now here we want to convert the remaining values in this first column. We want to convert the remaining values into zeros now. Here it should be 0 and here also it should be 0 now. Now therefore how it is possible now? Minus 2 plus 2. This minus 2 is in R2 second row and plus 2 comes from R1 now. Therefore R2 plus 2R1 here now. R2 plus 2R1 is a operation for second row. Next now. Here it should be 0 now. How it is happens now? R3 value is belongs to third row and the next here the 3 must be comes from R1 now. Therefore 3 minus 3 R3 minus 3 times of R1. Therefore the third row operation is R3 minus 3 R1 now. Now therefore here the values first row is same as it is. There is a no change in first row. Okay. In the second row there is a change. First we are taking the second row values, that is minus 2, minus 5, 7, 3, minus 1. After that now 2 times of first row, 2, 2, 8, minus 8, 3 is here. 2, 2, 8, minus 8, 6 it is now. 6 now. Now addition now. Therefore the sum is becomes now 0, minus 3, 15, 5 and 5 now. Therefore the entire second row values are becomes now 0, minus 3, 15, 5, 5. Here we have. Okay. And the next operation for third row now. What is the third row operation? R3 minus 3 R1 now. What is the R3 value here now? 3, 7, minus 6, sorry, minus 8, 6, 3. Multiplying the first row with 3. 3, 3, 12, minus 12, 9. Here these are the values. Subtraction value, therefore we are checking the opposite side. The sum is becomes now 0 and 4, minus 20, 18 and 6 now. Now therefore the entire third row is becomes 0, 4, minus 20, 18, 6 now. Now here it should be 1 now and here also it should be 1 now. For getting this 1 value now, what we are doing now, entire second row multiplying with minus 1 by 3 and entire third row multiplying with 1 by 4 now. Therefore 1 and it is become minus 5 and it is become minus 5 by 3, minus 5 by 3 and the next now, sorry, it is just a minute. Now it should be minus, no? Now 5 by 3 and 5 by 3. The last value is minus 5 by 3. Okay. Next now, the entire value divided by 4. Therefore 0, 1, minus 5. Next value 9 by 18 by 4 means 9 by 2 and it is now nothing but now 6 by 4 means 3 by 2 now. Okay. Now next now we are converting the values, the remaining values into zeros. Here it should be 0 and here also it should be 0 now. We are changing the first row values now. Okay. 1 minus 1. That means R1 minus R2. Okay. And the next it is now, it is also same now. R3 minus R2 now. R3 minus R2. Now, therefore, it is becomes now the column values. The first row values becomes now 1 minus 1 and 1 minus 0 is a 1. 1 minus 1 is a 0. 4 and 5 plus 5 9, and here subtraction of these two values. Okay, that is minus 17 by 3. Subtraction of these two values, 3 minus 5 by 3. Okay, it is minus 4 by 3. And after that, now next now second row is there is no change in second row, and third row values it is becomes now 0, and here it is 0 and it is also 0, and it is becomes 17 by 6 and it is minus 1 by 6 now. Now here now the complete the third row. Here if you converting into 0, here the entire third row is multiplying with 6 by 17 now. Therefore, the values are becomes, the third row values are becomes like this now. 0, 0, 0, 1 minus 17 now. Okay. Now, here observe the argument matrix now. What is the rank now? First 4 columns are represents for A matrix. There are 3 non-zero rows. It is a non-zero row because one element is non-zero element, and the remaining 2 also non-zero rows now. Therefore, number of non-zero rows are 3. Number of non-zero rows are 3. Therefore, rank A equal to 3. Rank A equal to 3. And rank, this argument matrix rank. Okay. Now here also we have 3 non-zero rows now. 3 non-zero rows. Now therefore, what is the rank now here? It is a 3. Therefore, ranks are same. Therefore, the given equation Ax equal to V is consistent. That means now roots are exist. Therefore, V is in column A. V is in column A. Okay, that is the first part now. Next now, I am taking one more example. A equal to 10 minus 10, 0, 1, 1. The second column values are minus 8, 2, minus 1, 1. And third column minus 2, 2, 6, 0. And the last one minus 2, minus 2, 0, minus 2. And W equal to 2, 2, 0, 2 now. Now determine W is in column A and is in column null A. The given matrix order is here now 4 rows and 4 columns are there now. 4 rows and 4 columns are there. Therefore, it is a matrix order is 4 by 4 now. Now, therefore, in W, there are 4 columns are there now. There are 4 columns. Therefore, definitely W is in null A. What about null column A now? Column A. For calculating column A, AW, first I am taking entire A value, 10, 0, 1, 1, first column. Second column, minus 8, 2, minus 1, 1. Next, minus 2, 2, 6, 0. And next, minus 2, 0, minus 2. And the last one is W. It is 2, 2, 0, 2. Okay. It is a W value now. The leading coefficient should be 1. Therefore, I am interchanging these two rows. That is first row and third row. I am interchanging these two. Okay. Now, the first row becomes third row and third row becomes first row. The first row value is 1, minus 1, 6, 0, 0. And the third row 10 minus 8 minus 2 minus 2 2 now. Now here the leading coefficient is 1, therefore convert the remaining values into zeros now. Therefore here it should be 0. Okay, how it is possible? 10 minus 10 is a 0 now. Therefore 10 is belongs to third row and 10 should come from first row now. Therefore 10 times the first row now. Therefore the row operation is R3 minus 10 R1 now. And the next now the row operation for column R4 is just a simple subtraction of these two. Therefore R4 minus R1. Okay, very simple calculation now. 10 minus 10 0 minus 8 plus 10 is a 2 minus 2 minus 16 minus 62 and remaining 2 are 0, therefore there is no change in last two elements, same as it is now. Second row, first row is same as it is, there is a no change. And next subtraction 1 minus 1 0 1 minus plus 2 0 minus 6 minus 6 and minus 2 and 2 now the second row second column element should be 1, therefore entire second row multiplying with 1 by 2, and similarly entire second and fourth row are multiplying with 1 by 2 now. Okay, now therefore it is becomes now the values in the second row becomes 0 1 1 1 1 and next 0 1 minus 31 1 1 and the last value 0 1 minus 3 1 1 no. Okay, now these are the conditions. Now convert the values into 0, these two, particularly these two values. What is the operation for R3? R3 minus R2. In R4, what is the operation? R4 minus R2. Therefore 1 minus 1 is a 0, 31 and 1 32, 1 minus 1 0 and here also 0. Next 1 minus 1 0, minus 1 minus 4 it is now, minus 3 minus 1 minus 1 and the remaining are zeros now. Now the entire third row multiplying with minus 1 by 32 and the entire fourth row multiplying with minus 1 by 4. The values becomes now 1 0 0 1 0 0. Here it is, and fourth row values are becomes now 0 0 1 0 now. Convert the remaining element, fourth row element, into 0. That is very simple operation. R4 minus R3. Therefore 0 minus 0 is 0 now. Therefore the first row is becomes non-zero row, second row non-zero row, third row is also non-zero row. The first four columns are for A and the last one is for W. Entire values augment matrix it is. Now here I am checking the rank value. In A matrix there are three non-zero rows are there. First, second, third. Therefore in A there are three non-zero rows. In A W there are same number, three non-zero rows. Therefore both ranks are same. Ranks are same. Okay. Now therefore the equation Ax equal to W is consistent. Therefore W is in column A. Okay, right? Okay, now that is the condition now. For the null matrix, just I am taking multiplication of the two. A into W is becomes now how it is, row into column, just this row into column 20, next minus 16 0 minus 4, and similarly if you take row into column, each and every element is becomes now 0 now. Now therefore W is in null A. W is in null A. Now similarly you do this problem now. Okay, let A equal to -2, 4, -1, 2, and W equal to 2, 1. Determine if W is in column A or not, and similarly the null A. Okay, work out cheyandi ఇది. Next now we'll discuss some problems, true false problems now, which is depend upon given definitions or properties or theorems now. What the first problem now? The null space of A is a matrix. We know the order m by n, general matrix. The null space of A is the solution set of the equation Ax equal to 0. It is a given statement now. The statement is true. Ax equal to 0 is nothing but a homogeneous equation. Ax equal to 0 is nothing but a homogeneous equation. These equation values are belongs to null A. Okay, this equation solutions are belongs to null A. Okay, now therefore it is nothing but now the given, as per the given statement now, the null space of A is nothing but the solution set of the equation Ax equal to 0. That is the condition now. Next now, the null space of an m by n matrix is it Rn. Now in the given matrix now, there are m rows, n columns. M rows, n columns. The given statement is a false statement. Why it is false statement now? Always the column space, the null space is a subspace of number of columns of n now. Therefore Rn, here it is now. The null space is a subspace of Rn, not for Rm now. The number of rows for column space is a subspace of R power m. That is the difference. So null space is subspace of number of columns. How many columns? N columns. Rn. It is a subspace of Rn. Now therefore the statement is false statement. And the next now example, the column space of A is a range of the mapping x to Ax. What is the given matrix now? X to Ax now. There is a function t of x equal to Ax. That is a mapping definition now. F of x equal to Ax. Okay, now what is the given question now? The column space of A is a range of the mapping. The given statement is true now. The given statement is true now. We are assuming the given matrix order is m by n. A matrix order is m by n. Okay. Now, generally the null space is a subspace of Rn and column space is subspace of Rn. Okay. Now, therefore, the column space of a matrix is nothing but now range of the mapping. Okay, it is nothing but now range of the mapping. Okay, second definition, third problem. Now it is the, if the equation Ax equal to b is consistent, then column A is in Rm. Okay, if it is a consistent, then column A is in the Rm. Okay, now what it is a statement now? As per the given equation, the statement is false now. Okay, the given equation Ax equal to b is consistent for some b values, only some particular condition now, for not in general condition now. Therefore, the statement is false. Why the statement is false? the given equation is exist for only some b values, not for all b values. That's why the statement is wrong statement. Okay. Now, next now, the kernel of a linear transformation is a vector space. Is a vector space. Yes, it is true. The given statement is true. Okay. The linear transformation, given linear transformation, in the given linear transformation, if any linear transformation is given, for example, t of x equal to ax like that now, definitely the kernel is of the linear transformation is a vector space. What is a kernel contains now? The similar condition, what is a null A? The similar condition now. What is a null A definition? X is a vector in null A. If any vector belongs to null A, it should be satisfies the condition Ax equal to 0. Okay. Now it is similar to kernel property. Therefore, the statement is true. And next now. The null A, column A, is a set of all vectors that can be written as Ax for some x. Okay. Column A is a set of all vectors that can be written as Ax for some x. Okay, now observe here now, the column A is nothing but the linear combination of A column, capital A matrix column now. Now the given statement is true. Column A is a linear combination of columns of A using X. Okay. For example, for first column into some value plus second column into some value like that now. Therefore, it is nothing but a linear combination as per the definition now. Okay, now next now, null A is a vector space. Definitely, it is a vector space. What is the first property here in the true and false now? Null space is a matrix in Rn. It is here. It is now subspace of Rn now. Similar type of problem now. The given statement is true. The null space is a subspace of Rn. Okay, subspace means it satisfies each and every property of vector spaces. Therefore, null space is a vector space. Why it is a vector space? Because it is a subspace. Subspace means satisfying all vector space properties. That's why it is null space is a vector space. The given statement is true. Okay, now. Next now, the column space of an m by n matrix is in Rm. Yes, it is a true. Okay. The column space is subspace of Rm. Okay. It is a subspace of Rm. Therefore, definitely it is belongs to Rm. Okay. Now, next, what is the condition now? Column A is a set of all solutions of Ax equal to B. Column A is a set of all solutions of Ax equal to B. If the given statement is false statement now. Column A is a set of all B that have solutions. We don't know whether it has solutions or not now. And one more point, column A is a linear combination of all columns of A. Okay. And the next now. Okay. Now we discussed different type of examples on null A and column A. And thanks for watching my videos. Thank you.